Jai Hind everyone. I am Amit Kumar, Assistant Professor Computer Science and Engineering Department, Ajay Kumar Garg Engineering College, Ghaziabad. So today's topic is algebraic structure in Dstl. Dstl, that means logic theory, discrete structure and logic theory. Here in today's session, we complete the lecture on group theory. So, the outline of today's topic is what is algebraic structure, what is properties of algebraic structure. We cover some properties of algebraic structure here: semi-group, monoid, groupoid, group and abelian group. So, these are the topics we cover today. The first we cover the algebraic structure. As we know that algebraic structure is nothing, is a type of non-empty set G which is equipped with one or more than one binary operation. One or more than one binary operation. Suppose that here G is any group, G is any set, and this one is multiplication operation. This one here is known as binary operation. So, this one is covered as a algebraic structure. So, this binary operation, under this binary operation, this set G is algebraic structure. We have more than one binary operation also here. G, this one is the addition, this one is the multiplication. So, we have more than one binary operation also. So, binary operation on non-empty set G and G star. G star, that means here, that is multiplication. We have many type of binary operation. So, we will known as algebraic structure. Here is an example of n, and is a natural number. Here is a natural number with the binary operation. Multiplication is an example of algebraic structure here. So, this one is a algebraic structure. This one is an example of. Next, another example, rational number and binary operation, here addition is a type of algebraic structure which equipped with two binary operation. Okay. So, this one is the dot operation here. Okay. So, first one is addition operation and second one is dot operation, is a type of algebraic structure which is equipped with two binary operation and dot. Okay. Dot is generally is denoted as a multiplication also. So, here we cover the two binary operation. So, one or more than one binary operation with non-empty set G is known as algebraic structure. So, this one is algebraic structure here. So, what is the properties of algebraic structure? So, one by one we cover it. Here, closure property. The first one is closure property, associative property, existence of identity property, existence of inverse element, commutative law and distributive law we have. So, as closure property that means, suppose that A that is an element of G and B is an element of G also, then A, this one is the binary operation here, A binary operation, B is also in a G. Suppose that A is an element of set G, B is an element of set G, then A binary operation B is an element of G. That means this element is in a same set, this known as closure property. Okay. So, when we said that with the composition table, with the composition table we can prove that all element of after the applying the operation, binary operation, is in a set. This complete the closure property. The second one is associative property. Suppose that A, B and C is an element of Z, then A binary operation B binary operation C is equivalent to binary operation B binary operation C. This one is equivalent to A operation B and C. So this one is known as associative. Okay. Existence of identity element. What is the identity element? Suppose E is an element of G. E is an element of G and A operation, binary operation E equal to A or E binary operation A. So if we have this type of a configuration or of this type of a calculation, so we can say that this A is an identity element. In group G we have an identity element. Okay. Let us say example that 3 multiplication by 1 is equal to 3. So here 1 is a identity element. If G has a 1, 2, 3, just like that, a set. So this one is a E is a identity element. So existence of identity element says that E is in a group, a such type of a element in a group that have, say, this type. This one is a have a binary operation E equal to A. Existence of inverse. Existence of inverse, that means when A binary operation A inverse, that means A inverse equal to E. So if we have this law, A binary operation A inverse equal to E, that means we have inverse property. Commutative law says that A and B, A is an element of G, B is an element of G, then A binary operation B equal to B binary operation A. Okay. So this one is known as commutative law. So one by one we can solve it. Distributive law. Distributive law, here right and left distributive. So one by one we can elaborate it. A binary operation B plus another binary operation here. So A multiplication B plus C. So we distribute this one. A multiplication B plus A multiplication C. This one is known as right distributive law. Here this one is known as binary operations. And left, B plus C multiplication with A is known as B is equal to B binary operation A plus, this plus is distributive, and C multiplication A. So this one is a left distributive law. So we have closure, associative, existence of identity, existence of inverse, commutative law, distributive law. So with these algebraic property, we can prove that this one is a groupoid, semi-group, monoid, group, or abelian group. So if any structure, algebraic structure, have this type of a property, they reflect their definitions. So next, here we can easily see that when any algebraic structure have closure property, that means if any set G have a certain element and applying the binary operation on a set, each result is also in a set that known as closure property. If the set G is a certain binary operation, have a closure property, then this one is known as groupoid or quasi-group. In a similar way, if a set non-empty set G in a certain binary operation have a closure property and associative property, both closure property and associative property, then this one is belong to semi-group. Here, if G contains closure and associative property with respect to any binary operation, so this one is known as semi-group. In a similar way, if any non-empty set G with respect to any binary operation have closure and associative and have an identity element, then this structure is known as monoid. So, if three properties we have, closure, associative and identity element in a set, so this structure is monoid. Similar way, if any non-empty set G have closure property with respect to any binary operation, associative properties, existence of identity element and inverse law, have an inverse law or an inverse element in a set, then this algebraic structure is known as group. So, if we have these four properties, then we can say that the structure is a group. And if we have a five properties, closure, associative, existence of identity, existence of inverse and commutative law, five properties, that structure is known as abelian group. So, one by one we can prove if only one property have closure, then groupoid or quasi-group. For two properties we have closure or associative, that means semi-group. The three properties, closure, associative and existence of identity element, this one is a monoid. If we have a four properties we have, closure, associative, existence of identity element and existence of inverse element, this one is group. And five properties we hold or satisfy the five properties with respect to any binary operation with non-empty set G, closure, associative, existence of identity, existence of inverse and commutative law, this one is known as algebraic structure. So, with the help of example, we can understand how we can solve this. So, here we take example, prove that this one Z6 and this one addition modulo 6. Addition modulo 6 is an abelian group of order 6. So, at first we know about what is the element of Z6. So, Z6 is 0, 1, 2, 3, 4 and 5. So, at first we draw a composition table. With composition table we can prove that this Z6 have a such type of a property, hold a different type of a property, and when we satisfied the different type of a property, then we can see that abelian group. So, when we want to prove the abelian group, we have a five properties. First one is closure, second one is associative, third one is existence of identity element, fourth one is existence of inverse element, and five is commutative. So, one by one we can prove that, and when we can say that the all five properties satisfy, so this one is a abelian group. So, at first we draw the composition table. So, this one is the composition table, 0, 1, 2, 3, 4 and 5. 6 element is there. So, this one is a, and this. So, one by one we can evaluate it. 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 0 plus 2 is equal to 2, 0 plus 3 is equal to 3, 0 plus 4 is equal to 4, 0 plus 5 is equal to 5. So if we want to add a 0 in each element, so we find this result. 1 plus 0, 1, 1 plus 1, 2, 1 plus 2, 3, 1 plus 3, 4, 1 plus 4, 5, 1 plus 6, 6. But when modulo 6, that means 6 minus 6 is equal to 0, then the result is 0 here. Okay, please see this. Similar way, 2 plus 0, 2, 2 plus 1, 3, 2 plus 2 is equal 2 plus 2, 4, 2 plus 3 is equal to 5, 2 plus 4 is equal to 6, and 6 minus 6 is equal to 0. 2 plus 5 is equal to 7, and 7 minus 6 is equal to 1. Please note that 0 and 1. In a similar way, 3 plus 0, 3, 3 plus 1, 4, 3 plus 2, 5, 3 plus 3, 0, 3 plus 3 is equal to 6, and 6 minus 6 is equal to 0, 3 plus 4, 7, 7 minus 6 is equal to 1, 3 plus 5, 8, 8 minus 6 is equal to 2. In similar way, 4, 5, 0, 1, 2, 3, 5 plus 0, 5, 5 plus 1, 6, 6, 1 is a 0, and 1, 2, 3, and 4. So, when we apply 2 plus modulo 6 here, 1 is equal to 3. 2 plus 1 is equal to 3. Again, 4 plus 4 under modulo 7. So 4 plus 4, 8. 8 minus 6 is equal to 2. So with the help of composition table, 4 and 4, this one is a 2. Result is 2. So we prove one by one property. At first we see the following observation. Following observation, the one is closure. For first property is closure property. So each element we see here, this find the result, and each element is in a set Z6. So we can say that the closure property hold. The first property, closure property hold. The second, suppose that we take a 3 element 0, 1 and 2, and a binary operation, we prove the associative law. So 0 plus under modulo 6, addition modulo 6, 1 plus 2 is equivalent to 0 plus 6, 1 under multiplication modulo 2. So we solve it. 1 plus 2 is equal to 2, and 0 plus 2 is equal to 2 is equivalent to 0 plus 1. So 0 plus 1 is equal to 1. 0 plus 2, 1 plus 2, 1 plus 2, this one is 1 plus 2 is equal to 3 here. So this one is a 3. And 0 plus 3 is equal to 3 here. Okay. So 0 plus 1 is equal to 1, and 0 plus 2 is equal to 3. So we can say that both are equal here. So both are equal here. That means we can say that our second property, associative law, also hold. And the third, existence of identity. So we choose an identity element here. We can say that in addition, a 0 is the identity element is equal to 0 here, because of 1 multiplication 0 is equal to 1. Okay. So and we can say that a same 0 plus modulo operation 6, 1 is equal to 1. So we can say that E identity element 0 exists in our group. So existence of identity element, that means third property also hold. A fourth property, inverse operation. Inverse operation is nothing, is say that when we apply 1 plus here 1, the inverse of 1 is 5 here, and this one is 0. and that is equivalent to E. Okay, in the same 2, 4 is equal to 0, and that is equal to E. So 4, the inverse operation of inverse element of 2 is 4. So we can say that the inverse property is also hold. The fourth property, inverse operation, inverse element is also hold. Therefore, we can say that if 4 property hold, this Z is a group. But if we prove that the commutative law is nothing, is if suppose that A binary operation B equal to B binary operation A. Okay, so A is equal to 1 here, and we take a 3 equal to 3 binary operation 1. So 1 plus 3 equal to 4, and 3 plus 1 equal to 4. So both are equal. Then we have satisfy the 5 properties: closure, associative, identity, existence of identity element, existence of inverse, and commutative law all. Therefore, we can say that this Z6 is a abelian group with respect to addition modulo 6. So I think you can understand better with the this example. Thank you.